Hello all. So in this session, I just thought of covering some general idea about FPGA prototyping. Nowadays, like it's becoming very you know uh, very big requirement. If you take any design, for example, if you take your ASIC RTL and if you're developing any new ASIC and you wanted to validate into the real hardware before you actually go to the silicon tape out actually. So if you design any of the IP level or any SoC level, so any design you do by yourself, okay, so it needs a proper validation, like to implement in the real hardware. So FPGA is a platform uh, where it is giving the flexibility to the custom design, such as ASIC, ASIC and the SoC, and so another aspective, like FPGA is a different hardware, right? So when you do design, like you don't target to any target to the FPGA in the first place. So what you target, you will just start writing your RTL code. Maybe you target for some general ASIC. So you may so use some ASIC tool to synthesize your design. For example, Synapsys VCS tool or design compiler. Use such a synthesis tool like to synthesize your RTL code, and then you see the netlist file and all, like how it is being synthesized and all. So if you take Synapsys tool, like it uses this standard cells concept, right? So and also like for your design, if your design has some IP level logic, right? So what do you do? So you use some IPs which are readily available, right? You don't have to develop everything. For example, if I'm developing some SOC, any ASIC RTL, so my design is something like this. My ASIC, sorry, okay. So I'm doing some maybe for example some signal processor or any memory, memory access something. So I do write some custom logic here, and so I need some dedicated block. For example, I want to do some signal processing operation. I can use some IPs which are already available in the tool itself, right? So in the library itself. So I use this to connect my custom logic to the IP, and somehow it connects like this. So these are like IPs, right? So which is like, for example, asynchronous IP or any signal processing IP you wanted to use it. So it's a common way, right? So you don't want to develop RTL for everything, right? So somehow you write a code and you can start doing the verification point of view. Also, this is my test bench I write it. So I just start doing the simulation here, right? So this is my DUT, ASIC DUT, right? So this is my DUT. So this is my test bench. Can you use system Verilog or Verilog? So it's always recommended to use system Verilog for the test bench purpose, and you can use Verilog, for normally design. It's very common practice. So Verilog is used widely, so you can use Verilog itself for your design. So now the thing is like you cannot directly go for your you know with this level. Okay, fine. Now I have done my design. I have done my synthesis point of view, and now you cannot directly go for this. Okay, now you can go for this implementation point of view. Maybe you can go to the backend tool and do the physical design and the implementation point of view. Do the layout, routing, everything. You can do it. Okay. So before, like you just did only the simulation level verification, right? So with your simulation level confidence, yes, my design is working fine, functionality is properly working, my ASIC design is functionally working fine. Only with respect to simulation, that much confidence I have it in my hand, right? Okay, from my team or from anybody. Okay, I have that confidence. Only at the simulation level, my design is going to working fine. I have done all the test cases, all the corner cases. I have written the UV methodology also for the verification purpose, and I am able to verify it, my design properly. Now I'm giving it to my backend tool, and it will do this. I'm giving my netlist file here. Okay, so I'm giving my netlist file. Any format you take it, maybe ED format, EDN format. It's common netlist format. So this will go to my backend tool side. My backend tool will do this in a placement and routing in the real silicon. I mean, in the tool itself, routing and do this timing analysis and so analog layout. So it does all the steps involved in the backend side. So this is my physical implementation in the backend side. I use the physical tools, physical design tools for this operation. I call it the physical design development. So once my layout is available, it will go for this real silicon chip. Okay. Of course, you will find lots of bugs even in the backend side, also including timing analysis and the cell placement. So you'll find all these techniques here itself, and we'll go for this real silicon bring up activity here. So once my silicon chip is available, so I can take it to my laboratory, and where I can download my softwares and connect all the maybe any external interfaces I'm doing it. Okay, any ADC, DEC, I2C level interfaces I'm doing it. So I can connect all the interfaces with my real silicon and start doing the same testing. Like it's called post silicon validation. So I will do this. Like I'm just giving you the idea and the real silicon validation. So I do all my testings with respect to my software, everything. So is this enough? Like for example, if I'm finding some bug which is not being captured at this point in the simulation point of view, and at the backend point of view, right? Here you don't do any functional testing at all, right? You do the cell placement. If any issues in the RTL, like with respect to timing analysis, and they will be able to tell you this point. So when you have the real silicon, suppose you're finding some bug here, something is not happening, like some design functionality issues happening. Okay, due to that, your none of the peripherals are not getting accessed. Our system is not getting reset. Okay, some reason. Okay, so now we come to the real silicon point of view. Now you cannot go back and change all my design again, come back to this point. Like it's very expensive method, right? It's very expensive method. Like once we get into the silicon, and it's not so easy to come back to the cycle again. Look back, what went wrong, and identify the bug, and again go back to this flow and bring a real silicon chip. So it's very expensive at that point of time, right? So I'm just giving you the overall idea. Okay, so before we go to that stage, so it is like when you do our simulation level verification, right? So it is this alternative platform, like we have it called FPGA platform, right? So you all must be aware of it. I'm just giving a like overview about it. Okay, so we have this FPGA platform. Like how does this FPGA platform work? It's at the hardware perspective. So FPGA platform is entirely different from the what you call like standard cell based environment, like the ASIC you're implementing, right? So it will use some programmable logic cells, like which means it can be programmed to any complex circuits can be programmed multiple times. You can program it and erase it. So it has that flexibility. So it gives you this programmable logic cells, which is called this configurable logic blocks. It will have many configurable logic blocks. Okay, now I have one idea. Okay, fine. Let me take my ASIC RTL after verifying in simulation test case. Let me take into the real hardware, which is called FPGA hardware, right? So before I go for my further process, my backend implementation and and then real silicon bring up activity. So let me take this RTL and place it on FPGA. So placing this ASIC RTL into FPGA like comes with a little bit challenges. Like my ASIC RTL is written mainly for the ASIC purpose. As I said, you may go for some IPs, custom IPs, macro cells, and also the clocking wise. If you take ASIC level clocking, the clockings are not, the clocking structures uh, is like it supports many clocks in ASICs. If you see, your design may have, more than 10 clocks, 20 clocks, right? So that many clocks you can have it. So the challenges will come because it's a if you have bigger designs, okay, minimum one clock you use it, okay, and maximum you go for two clock, three clocks. For some bigger designs, you have to go for minimum 10 clocks, 10 to 20 clocks. If you're taking any SOC night, so 10 to 20 clocks you will minimum going for it. So how do I take my clocking structure and place it in my FPGA platform? FPGA supports a different type of clocking, like global clocking. So these clocks are limited in FPGA platform, right? So this is one challenges. Number one is clocking. How do I place my clocking into my FPGA platform? Right, this one question will come in your mind. And the second thing, like how do I map my resources? For example, I use some, you know, memory implementation, for example, simple port or dual port RAM memories I use in my ASIC hardware. So now I need to map this RTL RAM into my FPGA. Otherwise, what happens? So you will end up in consuming more resources. When I say consuming more resources, like you will try to port your RAM RTL into your FPGA, it will try to use some common resources. Okay, so eventually we have lots of logic, and we don't want to consume memory to these logic blocks. It will end up, fill up all the resources. So FPGA provides some, dedicated blocks called this block RAMs. It's called BRAM or URAM in the latest FPGA PCH. It supports some URAM, which is little higher capacity than the BRAM. And also we have this distributed RAM. Again, I said it will be common resources. So we need to aim for this kind of memory resources. So we need to map this RAM into our block RAMs, dedicated block RAMs, right? So with the given options, we have to give you some kind of changes. We can't make a change in RT at the same time. So we have to provide some input to the tool, right? That you need to go and consume this dedicated block RAMs. Okay, so that we need to mention to the tool. Okay, so that's the one thing, memory and the reset wise, for example. ASIC may support lots of asynchronous reset environment. Of course, design will come with a lot of asynchronous reset environment, synchronous reset, mixed up resets, and you have to use some synchronous reset synchronizer and all for this asynchronous reset. For example, assertion kind of things happening. Okay, so we'll do this kind of things. For example, here also, like we have to know, we have to see how do we place our reset logic into our FPGA platform also. How do we do that? Resetting in the FPGA platform. For example, FPGA mainly supports like asynchronous reset is there in our design, but we have to see whether our which one is going to give you more efficient way of implementing. For example, for the time closer, for example, this kind of dedicated blocks, always supports synchronous reset. For example, block RAM and other blocks like DSP slices, which do the mathematical application, multiplication and division, all this mathematical operation done by DSP. So this all dedicated block supports synchronous reset. It provides the best optimization and the timing wise. It provides all kind of support in this environment. Okay, so and then like our IO standard, for example, we have some peripherals are connected, and we have to connect those peripherals in FPGA also. So we have to define these IO standards properly. So these are a common thing like we should take care when we try to uh, port our ASIC RTL into FPGA RTL. And then we have these IPs, and these IPs are not going to be pure RTL again, right? We are trying to take it from Synapses Designer IP or whichever tool you use. You're trying to use that IP only. So how do we replace this IP into FPGA platform? We have to find a way. How do we replace these IPs into an FPGA platform? So these are the common thing we should think about. Like before we say like I want to put my my code into my FPGA. It's not going to directly take as it is. Okay, we have to provide all this information to the tool, and then you have to map your RTL into FPGA. At the same time, changing the RTL is not a feasible way of if you start changing your ASIC RTL, right? So if you start changing your ASIC RTL because you want to map into FPGA, just imagine again you have to go back to your ASIC only. So you'll be keeping two RTL in your hands, and it is not it's not a feasible way of doing it. Like I don't want to touch my RTL, but I wanted to my tool to understand what it is up to. If I have to provide some alternative solution, alternative way of replacing these IPs, like how do I replace these IPs? Like any uh, any intermediate solution I can provide. Okay, for the tool to understand this information and start processing it. And finally, it will generate the netlist file for you. And then again, you go for this backend implementation. So once you go for this backend implementation and you will generate this bitstream format at last. So once you have the bitstream format, you can start testing it in the real hardware, which is your FPGA board. For example, if you have bought any FPGA board, you can start testing it on the real-time FPGA board, and you can start debugging also. How do you debug? You can just connect some real-time. It's called logic analyzer, where you can actually connect your all the signals similar to the simulation. Here we don't do the simulation point of view also. We directly generate your netlist file. So this backend will does this place and route for the corresponding FPGAs, and it will give you the bitstream file, bitstream format it will give you. So once you get the bitstream file, you will go to your FPGA. This makes real hardware, FPGA real hardware, okay? And I'm going to put it on my FPGA board. Once I paste it on my FPGA board, so I can get the visibility into my debugging environment. Like a simulation, I can do the visibility in the ILA platform. It's called logic analyzer platform. So where you can add all your signals, okay, your clock, your reset, what are the other inputs you have. You can, for example, you're debugging some DDR level or AXA level. You can add all the write data, read data, and all the write and read channels, and see how they are responding in the real-time hardware. Whether my functionalities are expected, working as expected. For example, I connected all my peripherals like Ethernet, USB, PCI. So I try to validate all my peripherals in my hardware. Again, this debugging is not like simulation, because you're doing it in real hardware, okay? And you cannot add lots of signals at the same time and do the debugging here, right? So it's not possible. So there are some limitation that what kind of some limitation in debugging, like how many segments you can add, and how much visibility you get, right? But in simulation, you can add lots of signals at the same time. You can start debugging it, right? But here in this FPGA platform, like we have some limitation, because we are using FPGA board. So there are some dedicated platform for prototyping, for supported by the Synapses and Cadence, and like they provide the good visibility platform, like full visibility. Sometimes you can get that prototyping platform, which is called prototyping platform. If you get those platform, you can get the like much better visibility than the single board you're getting here. Okay, this is another way. This is entirely to the debugging point of view. Okay, so this is the overall idea, like why the prototyping is important and why you're choosing the FPGA platform here and all. Okay, so and I told you what are the different types of things should be taken care before we actually move into the platform. Okay, so this is a basic idea. I just wanted to give you the introduction about it. In this section, I just wanted to you know give a little importance to this clock gating. How does the clock gating has been done in ASIC and FPGA? Okay, so like if you are doing any ASIC design, you must be aware of it, how the clock gating is done in the ASIC platform, right? So I'm just going to erase all these things so that uh, I can show, I can draw the. Just let me erase all these things. Okay, so what is the clock gating? Clock gating in the sense like so before clock actually going into it. So what do you do? This is my register, you can call it. Okay, this is my clock port. So now generally what we do, we directly connect the clock to our clock port. Okay, this is my clock port we connected. When I say clock gating, like what we do, we add some clock logic, maybe a gate logic. Okay, and then we'll give it to the clock port of the register. This is the general clock gating point of view. This is my clock port now, and this is my, I will give one enable signal. Okay, I will call it as enable signal. So now what's the advantage of this by doing this clock gating? So clock gating, we don't want our circuit to drive the clock continuously all the time. So I want my circuit to drive the clock only when there is a need. to operate this circuit part. Maybe my part of my circuit. Maybe don't assume this is the main clock. This might be my fifth clock or 10th clock in my design. I don't want this part of the circuit to be activated all the time. Like I want this circuit to be activated only when there is an operation. There is an operation to be happening in this circuit, right? So remaining time just to stay static, stable. Okay, no operation, no clocking transition. So how does it help? It helps in many ways in the real silicon. If you see, right, if you can control this clock transition. Clock means what? Like high, low, high, low, high, low, right? So every time high, low, high, low, high. This is the clock transition. So if I can control this clock transition, I can save a lot of power. It's called dynamic power. We can save a lot of dynamic power in my operation. So for example, if you say this enable can control it. I can pass this enable from my system level understanding. Whenever there is enable is needed, at that time I'm going to issue my enable. So only when enable is available, at that time only my clock will be passing to the rest of my circuit. I have this sequence of circuits after this point. So only at that time only my clock will be flowing through this circuit level, right? So the operation will be normal. So this is the advantage of clock gating. Okay, so there is a disadvantage, like if you use this gate level clock gating, it will create some glitches suddenly. Suppose if you're activating this enable in the middle of the clock, okay, so you don't get to see the full clock. The clock period will be cut it down. Okay, it's called glitches, right? It's a combination circuit, right? So for that reason you can go for some register based clock gating, whichever is possible. So that will give you the complete flexibility in implementing the clock gating. So now, how my FPGA will understand this clock gating? Is it okay to implement this clock gating in my FPGA directly? That is the point I'm going to cover now. So my FPGA design is not going to take this clock gating as it is. My FPGA design. So this is my clock gating, and this is the clock gating in ASIC design. Okay, so this is my clock port. This is my clock input. This is my enable input. So my FPGA design is not going to take this clock as it is. If you directly place this design into FPGA, okay, so what happens? It will start. I mean, same thing. Like it will go like this. It will try to implement this logic in the. It's called LUT. This gate will be mapped into LUT. Okay, in ASIC you assume it's a standard cell. Okay, just giving you the idea. Like it's a standard cell, like SC. It's a standard cells. If you look into the ASIC, it is called standard cells. If I directly map this logic into my FPGA, okay, so this will use the LUTs to implement your logic. And this is my clock input, and this is my enable input. So there is a buffer, it will add, and there is a buffer, it will be add. And this LUT will go to the my register. Register will have this clock port. Okay, so FPGA will have an additional port called clock enable. Okay, so by default, it is expected by the designer to make use of this clock enable port. But as if we don't have it, like we use this external clock gating methodology only, and there is a data input port. But in FPGA, we have this clock enable port, right? So as a designer, the tool is expecting us to utilize this port, the clock enable port, effectively, right? So now how do we convert? We don't want this LU to the infer and then it goes to the clock, right? So what's the problem? Like problem is something like it may add some, when we do some timing analysis, it may create some skew, like in the combinational path, right? In the clock path, we have some combination path also here, right? Because the clock is coming and if this is the data path, this is the clock path. We're just mixing these paths, and this will create some combination delay at the same time if you're entering into some skew and all. So during timing analysis, it's going to be a very big headache for us. Since FPGA already providing this platform in the flops, if you take any FDC flops, right, you can see this additional port in FPGA. Okay, so I can show you if you want. Let's just see FPGA FDC flop. Let's just look at the image. Yeah, if you see this flop, right? So this has this clock enable, right? So if you see there is a data input and there is a clock input, and there is an additional input called clock enable. This is the it is called FTRE. Okay, it's FTRE register. Okay, so this is what I'm talking about. So in FPGA, so we have this default clock enable port. So we have to make use of this clock enable port, like to implement our clock gating. We have to move this the gating logic into the clock enable and let the clock to connect to the clock directly here, right? So clock and the clock enable, it will act as the clock gating in environment. So, okay, now how do we do this in the tool? As I already told, I don't want to touch my RTL, I don't want to touch my ASIC RTL for this reason. So the only option is something like we have to deal with the tool. For example, we can try writing some constraints, and the one point is XTC constraint, STC constraint. You're all aware of the constraint, right? We need a constraints in a FPGA platform. For example, IO constraints or the clock constraints. We'll provide all the constraints, and then we can go for some attributes. What are these attribute does? So these attributes we can directly add it in the RTL itself. Only the attribute we can add. Okay, we are not modifying the RTL here. I'm just adding this attribute. For example, if I'm going to make my clock signal as my clock gating, I can add this attribute to make clock signal that I can do. So I have the clock in my design. I can add this attribute. This attribute means like, for example, if I'm going to do my clock gating, I can add this gated clock attribute to my clock signal in my RTL itself. This is the second option. And there's one more option. There is a synthesize tool settings. Okay, synthesize tool settings, something like my tool will give you some option like you need to enable this gated clock conversion, right? So if you enable this gated clock conversion, the tool will understand it. There is some clocks are going to be there, so you need to consider them as a clock gating and convert this logic. So you don't have to do anything manually. Okay, so when you provide this clock as your constraint, for example, I'm giving this clock as my constraint. My clock, this is my CLK port, clock port. I'm writing one create clock constraint here. Okay, and then uh, one thing, you can write a constraint directly, the tool can understand directly. Okay, when you enable this synthesis option, this is compulsory, you need to enable this synthesis option. The tool will understand that this clock should be treated as a clock gating. So if you see the ASIC RTL has this logic, the gating logic, the tool itself will directly connect the clock into registered port, right? And this gating logic will go to the clock enable port. So there will be buffer in the middle, you can see some input buffer, so you can see some buff G in the clock path, and for this gating logic only the input buffer will be there. So this will be directly going and connect to the clock enable port. So this is the general way the tool will understand itself and implement it if you give it a constraint. If you have the more than one clock, right? In some time, in some cases, we'll have more than one clocks in our constraint. Okay, so clock one, clock two, and all I'll have it. Okay, so I don't have to do the clock gating in all the clocks. Sometimes, some cases, so we can write the attribute in the RTL itself, which clock should be considered for the clock gating conversion. So you can write this attribute in the RTL module itself. So tool can understand with respect to this option is enabled, it will start converting it. It depends on the scenarios you are giving. So I'm just giving the general scenario. How does it it's getting this is the way it will get converted and map into. These are the different options. The tool can use it to convert these options. Okay, so this is one way. So there are some other scenarios also we can see it. Okay, this is one scenario. I'm just going to tell you. So we can use some AND gates. So for example, more than one AND gate also sometimes comes, right? So in that case also the tool can understand and start mapping with the clock enable port with maybe the LED will come in the the gated logic path, and the clock directly will go and connect to these flops. So this is another scenario when I have multiple complicated logics, little complicated logic on top of it. The tool will understand and start mapping it. So this is my another scenario. Also, I can do it for the clock divider. For example, any one more scenario we want to just look into it. What is the one more scenario? Something like there will be some kind of derived clock. For example, some kind of derived clock. For example, I will have this clock input. I have this clock divider module. Okay, my clock will be divided by two here, and I will have this derived clock. Okay, So this clock will go on connect to my logic here. Okay, so this how do we deal with this kind of derived clock? We need to write additional constant called clock generated clock, right? So this is called clock generated clock. So we need two constraints, clock generated clock. So if you apply the clock gating, so in this environment, this derived clock, right? So it will go and connect in the clock enable path. So in this situation, like we're expecting, for example, this clock may connect. This is a real clock, okay? This clock may connect into the one part of the circuit, and this clock will drive the other part of the clock. Okay, so we are just applying the clock gating at this derived clock path. This derived clock path, we are applying the clock gating. When you apply the clock gating, it will shift to the clock enable port, right? So that happens. So during that time, like the constraints we are writing might go wrong, so the tool will give you some different inference, and maybe it may try to use the same clock to this place, and this will go into the clock enable port. So in that case, the circuit may not operate in the clock frequency we wanted it. Okay, we're expecting it to operate in the half of the frequency, but unfortunately, when you apply the clock gating, what happens? When you apply the clock gating, the tool assumes it's a gating logic because we are just doing the divide by two, right? It will use some LUT inside, like to divide by two logic. LUT inside or register inside. Okay, register inside. It will use it, and what happens? The tool assume it's a clock enabled path. Okay, so in that case, we have to just modify the constraint that we cannot do it at the beginning. We need to understand what is the alternative path that the clock is coming. Okay, so with that we need to get this new clock name and do this division operation. Once again, we change the constraint with respect to this new clock name and add the constraints, and then only the circuit will work as expected. This is rare scenario, but when you do some clock generation thing and applying the clock gating, just be very careful. You need to modify the constraint. You know, after synthesis point of view, after little implementation, you have to modify that constraint. The tool will give you the constraint point of view. This is another scenario. So as I told you earlier, there is a way we need to do it with the registers, right? Instead of using AND gate or gate, we can do the clock gating with respect to register also. So how does that works? So we can do it by registers also. How does that registers work? I'm just cleaning up everything. When I say registers, I said some glitches issue may arise, right? So for example, I have one register here and I have another register here, and this is my clock input. This is my data input, right? So data input, and this is my output, data output. It will go and act as a clock here. Okay, it will go and act as a clock here. Earlier we saw it's with respect to gates. Now we are seeing with respect to register itself. Okay, this will go and act as a clock here. It's again like derived clock kind of thing, right? So how do we map this kind of information into the how do we tell the tool if you apply the clock gating in this place, how does it get implemented? For example, if you apply the clock gating in that place, so I expect my clock to be connected here, and this is my input, right? So I take my input here, so this is my output. So I tell my tool, when you apply the clock gating, the tool understands and apply the clock gating logic here itself. Okay, this is my LUT now. Okay, instead of directly connecting the output, it will go via the LUT. Okay, and then it will go to my clock enable port. Clock enable port, right? This is my clock enable port, and this is my clock input. So, this clock will again connected to this clock, this register. Okay, so in this case, we are completely changing circuit. Okay, the tool understand and apply the clock conversion. How does it changing? It uses the same clock from this clock to this clock only. Only the input path. It adds the LUT with respect to the output. It's a gating logic, and that goes to the clock enable port. Right. So this is how it will change it. This is how it will change it. Yeah, so these are the different scenarios. I think there won't be, these are the different scenarios, like when using the gate level. I mean, we're using the gates and the registers and using any clock divider circuits also. Different scenarios where we can modify this, clock gating into our FPGA platform. So yeah, yeah, I think this is we covered all the scenarios which will be useful while doing this ASIC to RTL. So similarly, like if you use any other tool, right? For example, there are other tools also. So if you use Xilinx FPGA and you tend to go for this Xilinx option, like they provide this option like Vivado. I mean Vivado. You can directly take your ASIC RTL. Again, Xilinx does not support this kind of design where IPs, any standard cells or nothing. It won't support at all. So in that case, suppose your design has like this kind of IPs. If you're writing a simple design, for example, any IP level development you're doing, only you're using this ASIC RTL. Everything you're writing by pure RTL, and directly use this word tool, and the tool can understand. Just enable this clock gating option, right? And the tool will understand and convert everything, including reset logic, memory mapping, everything will be happening, right? You can just go through the log file also. Any warnings are created. For example, it's not able to map properly. Any memories are not able to input properly. So you can get all the warnings in the Vivado itself. Suppose if your design has the standard cell logic and the designer IPs, so the Xilinx, Vivado tool won't take this kind of inputs. Okay, it won't be able to compile this kind of inputs. Okay, so there are some other tools also like Synapses itself provide. It's called Simplify also. Simplify also you can use it. Simplify is again for FPGA synthesize purpose, but Simplify won't do this. Won't do this backend implementation. For example, bit stream generation happens only in the backend implementation. So what Simplify can do it? Simplify can take your RTL, like including this designer IP, standard cells, you're supporting everything, and you can enable your clock gating option, right? And write your synthesis constraints, everything, and it can do the synthesis operation and generate your netlist file here. So with this netlist, you can go to some backend tool. You can go to the now you can go to the Vivado. So Vivado will take it. It will be like a technology specific, netlist file, because when you do synthesize, you have to specify which device you wanted to implement at the final. So you will go for this Xilinx FPGA. So you will have to mention the FPGA family. So the netlist will come in the form of technology dependent netlist. So which FPGA device you want to go for it. So once you get the netlist file in the ADN format or AD format, you can go to the Vivado backend tool implementation. So it will do this. You have to give again the constraints and the input output constraint, any timing constraints you want to mention. You have to mention all the inputs and clock constraints. So all the constraints should be taken care. Any peripherals you're connecting in the hardware, all the IO constraint, IO standards should be taken care. So once everything is taken care, you can start implementing in the Vivado backend tool. It may take some time, and it depends on the design complexity. So once your design is ready, it will give you the bit file format. So the bit file you can directly put in the real hardware and start debugging your design. This is another way of doing it. Okay, so not every design you can directly take it into Vivado and do it, right? So when you have this kind of like IP level and macro cells, standard cells, everything you have it, you just directly go for this another tool, Simplify, and use the tool, and then you go to your tool, right? This will help you in solving those issues. Okay, this is the topics I just want to cover. I think it gives a little bit clarity. uh, we can continue to see more on this topic. I just want to give you the overview about it, and a little clarity about the topic and what people are doing, and why it is important. What are different options we can try for it, and we can cover other options also, other topics also in subsequent discussions. Okay, yeah, yeah. Thank you all. Bye.